This video discusses how to find the limits using the dividing out method, or in other words, by factoring. But before that, we will look at a quick overview of all the analytical methods that we are going to discuss during this lecture and the next lecture. Under the analytical methods, we will discuss how to find the limits using the dividing out method. That will be our first analytical approach. Dividing out method is also called evaluating limits by factoring. And then we will look at a theorem, which is also kind of an extension of the dividing out method. So the theorem we are going to see is limit x approaches to a, x raised to the nth power minus a raised to the nth power divided by x minus a. You can see if you directly substitute, the numerator is a to the n minus a to the n, which will be equal to 0. The denominator is also a minus a, which is also equal to 0, which means we have an undefined form. We can prove that this result is going to be equal to n times a n minus 1. We will derive that equation and we will discuss a couple of examples in our next video. After these two methods, we will discuss a third method called rationalizing. We rationalize the irrational functions. So I will simply write it as the rationalizing method. And then we will look at the trig limits, the trigonometric limits. There will be two theorems associated with the trigonometric limits. And finally, we will also look at the limits at infinity. All right, that's an overview of all the analytical methods that we are going to discuss during this lecture and maybe the next two lectures. Today, our plan is to work on the dividing out method, or the method of evaluating limits by factoring. Before discussing any of those methods, I just need to revisit the basic idea of limits. So we have three possible forms of limits. We can have limits of the form limit x approaches to a from left-hand side f of x. We can have limits of the form limit x approaches to a from right-hand side f of x. Or we can have limits of the form limit x approaches to a f of x. So this third one does not specify whether x approaches to a from right-hand side or left-hand side. We can do that only if the left-hand limit is equal to the right-hand limit. In such cases, we don't need to specify whether x approaches to a from left-hand side or right-hand side. Let's first look at this one real quick. X approaches to a from left-hand side f of x. What does that mean? We know the first thing, the reason why we write it like this. X approaches to a is because x is not equal to a. That's the first property. The second property is that x is very, very close to a. What's the third property? When you look at the left-hand limit, it also means that x is less than a. All right. Now we will look at the second case. For the second case, I need x to approach a from the right-hand side. And then I need to find the value of f of x. This means x is not equal to a. That's why we write it as limit x approaches to a from right-hand side. The second one is that x is still very, very close to a. The third property is, since we are looking at the right-hand limit, we know that x is larger than a. All right. And then when the left-hand limit is equal to the right-hand limit, we can simply write it as limit x approaches to a f of x. What does that mean? Basically, yes, the first thing is that the left-hand limit is equal to the right-hand limit. However, when we have limit x approaches to a, we need to first understand that it's about x being not equal to a and x being very, very close to a. whether x is greater than a or whether x is less than a, that information is actually irrelevant for this case. When the limit exists, or in other words, when the left hand limit is equal to the right hand limit, we don't care whether x is greater than a or whether x is less than a. In either case, we must get exactly the same value for this limit. All right, let's keep those things in mind. And then we can look at the evaluation of limits analytically as well. However, if you revisit these three things, we can see something in common. For all three of these cases, we have x being not equal to a. And also, in addition to that, for all three cases, we can see that x is very, very close to a. Because x is very, very close to a, even though x is not equal to a as well, first starting point of evaluating any limit is the direct substitution of a in the function f of x. When you directly substitute x equals a in the function f of x, if it leads to one of the undefined forms, what are the undefined forms? Such as 0 divided by 0, or maybe infinity divided by infinity, maybe 0 times infinity, maybe 0 raised to the 0th power, maybe infinity raised to the 0th power. Likewise, there can be some more undefined forms, such as infinity minus infinity. If you ever encounter any of such undefined forms while directly substituting the value of x equals a in the function f of x, then we go for alternative methods of evaluating limits. One alternative method we already discussed, which is the numerical method that was discussed during our last lecture. The numerical method will universally work technically for any limit problem. However, they may also be considered as a little bit of inefficient approaches because we have to substitute numerical values and do some further calculations. Therefore, they have also developed analytical methods. However, once again, if the analytical methods fail, one very easy approach is to go back to numerical methods. However, in the exams, if I ask you to do analytical approach, you have to do the analytical approach. In fact, the analytical methods are very, very popular. Therefore, you are expected to know the analytical methods thoroughly. So, the analytical method that we are going to discuss today is dividing out method, or in other words, evaluating limits by factoring. We will discuss this method using an example. Let's say we need to evaluate the limit x approaches to 2, x cubed minus 8 divided by x squared minus 4. Well, this was one of the questions that we already evaluated using the numerical method. But today you will see that this can also be evaluated by factoring. In fact, for this question, there are other methods also available to evaluate the limit. Today we are going to look at the dividing out method for this problem. So, as the name indicates, we actually have to start by factoring. Now, this is also a good time to revisit some factoring from college algebra. Can you remember the factors of a cubed minus b cubed? A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. What are the factors of a squared minus b squared? This is a minus b times a plus b. Of course, for this question, we just need those two forms of factoring. However, I will also write down the factoring for a cubed plus b cubed. It may be useful in the future with some other questions. A cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. All right, now get back to this question. We have to evaluate the limit x approaches to 2. The numerator, I'm going to write it as x cubed minus 2 raised to the third power. And the denominator, I'm going to write it as x squared minus 2 squared. However, I think I forgot to mention one quick comment. The very first thing that we have to do with a limit problem is to see whether the direct substitution works. Now, this is a question on limit x approaches to 2. So, the direct substitution is x equals 2. We know that x is actually not equal to 2 when we talk about limits, but we also know that x is very, very, very close to 2. Therefore, we would like to try the shortcut of directly substituting that value 2. Well, if I do that, 2 to the third power minus 8 is equal to 0 on the numerator, and on the denominator we have 2 to the second power minus 4, which is also equal to 0. So it leads to a 0 divided by 0 situation. Therefore, the direct substitution fails. That's why we try the alternative methods. And here we are trying the dividing out method. All right, back to this problem. First, I will write down that limit x approaches to 2. The numerator can be factored using a cubed minus b cubed factoring with a equals x and b equals 2. Therefore, the factors on the numerator should be equal to x minus 2 times x squared plus 2 times x plus 2 squared, which is 4. The denominator can be factored as x minus 2 times x plus 2. All right, what's next? How about cancelling off x minus 2 with x minus 2? Can we do that? Well, of course we can do that because we know that x is not equal to 2. X is only very, very close to 2 when you evaluate the limit x approaches to 2. Therefore, x minus 2, even though it's very small, it is not equal to 0. Therefore, I can perform the operation of dividing out x minus 2 on the numerator by the x minus 2 on the denominator. And because of this reason, it is not dividing 0 by 0. All right, everything is good. Now we have this part of the function remaining. We can try the direct substitution at this point. When I substitute 2 on the numerator, I will have 2 squared, which is equal to 4, plus 2 times 2, which is also equal to 4, plus 4. So the numerator is equal to 12, and the denominator, it will be just 2 plus 2, which is equal to 4. So this reduces to be equal to 3. All right, that was exactly the same answer that we obtained using the numerical method as well. All right, would you like to try another example? If you need another example, here is one. Let's say we need to evaluate the limit x approaches to, let's say this time negative 2 from plus side. Let's say the function I have is numerator, I have x squared plus 6x plus 8, and for the denominator, let's say we have x squared plus 12x plus 20. How would you evaluate the limits here? I will try the direct substitution first. On the numerator, I will have negative 2 to the second power, which is positive 4, and plus 6 times negative 2, which is negative 12, plus 8. That will be simplified to become a 0 on the numerator. And the denominator, negative 2 to the second power, is a positive 4. 12 times negative 2 is negative 24 plus 20. That will also be simplified to become 0. Therefore, the direct substitution fails. Therefore, we need to go for the alternative methods. And in this video, we are working on the dividing out method, or in other words, the factoring method. All right, let's go ahead and factor. Limit x approaches to negative 2 from plus side. What are the factors on the numerator? Well, the factors on the numerator are x plus 2 times x plus 4. The factors on the denominator are x plus 2 times x plus 10. We can see that x plus 2 is a common factor on the numerator and on the denominator. We can divide them out, and it is not 0 divided by 0 operation, because we know that x is not equal to negative 2 because we are evaluating a limit. In fact, for this specific case, x is slightly more than negative 2. All right, now we can do the direct substitution. When I put negative 2 in this remaining component of the function, on the numerator, I get negative 2 plus 4, which is equal to positive 2. And on the denominator, I get negative 2 plus 10, which is equal to positive 8. This can be reduced, and our answer is therefore equal to 1/4. All right, so that's it about the first analytical method of evaluating limits, the dividing out technique, also called the factoring method. Thank you so much.